So first I will just talk briefly about habitable zones and how I'm defining them for this talk. Basically there are obviously a lot of factors that could go into play when you discuss what defines a habitable zone. It's like, I feel like it's, okay. It is on, yeah. Okay. I'll choke on this. All right. Is that better? Okay. Okay, so basically we're approaching this idea of habitable zones from the astrophysical side. So, you know, we have different stars that are different masses and different temperatures, and so that's going to directly affect the location of a habitable zone around the star. And for stars of different mass, these habitable zones also expand outward at different rates based on the stellar evolution. So we're trying to basically quantify how these stars change over time and thus how the habitable zones change over time. So the two physical parameters that we can measure about stars are their mass, and that affects its rate of hydrogen fusion, and thus the main sequence lifetime. So that is main sequence. And so the more massive a star, the shorter lifespan it's going to have on the main sequence. And the main sequence for non-astronomers is basically just when a star is burning hydrogen in its core. So it's about 90% of a star's lifetime. It's really stable and long. Also composition, so what the star is actually made of. Now, stars are mostly hydrogen and helium, but they're also made up of other heavier elements, and differing combinations of these elements actually affect the opacity in the star, which affects the energy transport. So if you have a high opacity, you're going to have, you know, photons being generated in the center of the star running into more material as they try to get out. So if you have a higher opacity, you're going to have less efficient energy escape. So if you have less metal, you're going to have lower opacity and more efficient energy escape. And so two stars of equal mass, if they have different compositions, can actually, you know, change the lifetime of the main sequence significantly. So basically this is just to show how the stars change over the main sequence. So this is time in billions of years, and this is luminosity. So luminosity is just the brightness of the star. So for 5 different compositions here, black is just solar composition. You actually see that the lifetime can be significantly truncated versus, you know, a sun lives about 10 billion years. So something with, you know, about half the oxygen of our sun, let's say, lives about half as long. So really we're seeing, and it's much brighter. So there's a lot of different things that come into play here, and I'll talk more about that. So to model stellar evolution, usually astronomers say, okay, there's a metallicity in the star, and they compare it to the sun. So if you measure the iron abundance, they just assume that all the other elements scale in the same proportions that are found in our own sun, but that's actually not correct. Specific elemental abundances vary drastically between stars. In particular, oxygen we found significantly affects the stellar evolution. So, you know, the location and lifetime of the habitable zones are dependent on the host star, like I was saying. So if we take into account this extra oxygen factor, that's going to play a big role. So what I've been doing is just use the stellar evolution code Tycho. I've been creating a big catalog of all these different kinds of stars, evolutionary tracks, for different compositions. I've made a grid of 376 so far. Masses between 0.5 and 1.2, so kind of sun-like mass stars at different metallicities. So that's that just solar abundance value scaled. And then oxygen values, I have 2 depleted values and 2 enriched values, and those are based on actual observations of nearby stars. So we get something like this if I put something all together, some of my output. This is called a Hertzberg Russell diagram. It's just temperature versus brightness, or the luminosity. And we have my cool low mass stars on this side and my hot high mass stars on this side. And even within each of these colors represents a different mass. You can see that there's a large spread in the temperature and the brightness based on individual compositions. So you have to look at both. You can't just look at mass or composition to really get a full idea of how a star is going to evolve in its temperature and brightness over time. So, we care about temperature and brightness. Oh, this is just my little test to show that this is the sun, and it falls right on the solar track. So that's a good test for our code, make sure that it's outputting properly. But we care about, temperature and luminosity because at each time step, Tycho outputs these surface temperatures and luminosities, and we put them in to this program I wrote to calculate the habitable distances based on equations from Ravi Kaparapu's group. And I won't go too much into this, but basically I just wanted to show that these equations take in an effective temperature and a luminosity, and that's what our code outputs at each time step of its evolution. So we can actually calculate this D value, this habitable zone distance, for every point in a stellar evolution track based on these two parameters. And so we ultimately end up with habitable zone limits. The optimistic cases we don't really consider because they're optimistic. We want to be more conservative. So we take the runaway greenhouse to the maximum greenhouse cases, and that's just inner and outer habitable zone limits based on atmospheric properties of hypothetical planets that would be there. So if I plot my results based on those limit equations, I get something like this. So this is, again, age in billion years and distance along this axis. And blue represents the sun, or like solar composition. So we have inner limits and outer limits. So 1 AU is plotted for reference, so Earth is about right there. And so we're at the very inner limit of the habitable zone. The red is for about half the oxygen value. So if the sun had less oxygen, we would actually be too close. So this limit would be outward, and we would be too close to the sun to maybe host liquid water on the surface. So again, we also want to consider the cold start problem, which is that we want to avoid planets that have recently entered the habitable zone, because if something was frozen and then the star moved its boundaries outward and then it was at the right temperature to host liquid water on a planetary surface, we don't know if that planet would have the impetus to maybe unfreeze itself and host liquid water. So this prompts us to constrain the habitable zone with time criteria as well. So this was our first kind of iteration of this idea. So we have the zero age main sequence and the terminal age main sequence. That's just beginning and end of the main sequence. And that's in blue and red. And then the inner boundaries are solid, the outer boundaries are dashed. So this overlapping green shaded area is what would be called a continuously habitable zone. So where a planet in this green shaded area would remain habitable for its entire main sequence lifetime. However, if we plot Earth on this plot, it doesn't quite fall into that region, so we figured that that's not really a robust enough method of trying to understand habitability. So instead, we consider this continuously habitable zone of a 2 billion year minimum. So now the shaded green represents a planet at a distance in this green area would remain habitable for at least 2 billion years. And so that's obviously an anthropomorphic boundary condition that we've imposed because it took Earth about 2 billion years for life to produce a detectable biosignature, but it's a starting place at least. So we can now plot Earth and it falls nicely in our little shaded area. So basically this is just to show how we're trying to constrain our habitable zone time limits. Now this is just a little overwhelming, but it's basically the same thing as last plot, except that this is for all of my 376 stars. So each line is a different data point. And this is just, again, to reinforce the idea that composition really affects where your habitable zone distance is going to be. So if you have a distance here and you have oxygen and, okay, so let's just look at the solid lines even. There's a span in these elongated solid lines, and that represents that spread in oxygen values that we're looking at. So even a star of the same mass with different oxygen is going to have a habitable zone that's at a different distance. And so that would affect where the planets could be habitable. So this, I just wanted to point out that the fraction of time a planet would spend in the continuously habitable zone versus the entire main sequence is much higher for low mass stars than for high mass stars. We actually don't see any because these stars are so short-lived that there's no continuously habitable zone for 2 billion years. So that's one of the reasons why looking at low mass stars is really important. And it's going to help, further quantify what kinds of stars we should actually focus on in the future with upcoming missions, to try to look at planets and search for possibly inhabited exoplanets. So my next steps are basically just creating more data points to put in this catalog. We've made this catalog available online, and you can basically go on and put whatever tracks you want, and it'll interpolate different masses or different compositions and give you a habitable zone based on whatever input parameters you want. I'm also going to do the same kind of calculations for carbon and magnesium because those are also really important for stellar evolution. And we're also going to look at the late stage evolution beyond the main sequence because that should be really important as well. And we're also going to expand the catalog to include stars of even lower mass, so down to even like the brown dwarf limit, because they're very abundant and they're very good. They're very easy to detect planets around. So those are really good candidates to look for habitable planets. So thank you for your attention.
There are a couple eager ones at least.
Where am I going first?
Sonny.
So, 2 questions. What was the time difference from your highest mass, I guess, entire main sequence lifetime to your lowest mass? What was the time difference? So how long is the main sequence lifetime for like a 1.2 solar mass versus a 0.5 solar mass?
Yeah, so it's on the order of like 5 billion years for the 1.2 up to about 100 billion years for the 0.5. Okay.
And then my second point was that actually if you do look at the evolution of the solar luminosity with time, there is some suggestion that after about 1 billion years, the carbonate-silicate feedback cycle on the Earth will be insufficient to maintain clement conditions on the Earth. So that's why after, the entirety of the main sequence lifetime of the Sun, the Earth is not in the habitable zone.
Right. So. And that's, obviously it's a very complex problem, and we're just trying to approach it kind of from the bottom, constrain it from the astrophysical point, and then kind of collaborate with geophysicists and people who could tell us more about the actual planet side, as opposed to we're just coming at it from the star side. But yeah, there's a lot to consider with habitability. So.
Is here. Really nice work. I have 2 questions. I've seen some of the habitable zone gets really close to the central star when the stellar mass is small. I was wondering, do you need to worry about the irradiation of high energy photons in that situation?
Yeah, we're actually, part of our next steps that I didn't include on the slide was actually looking at M-dwarf age versus activity. And so that would be the lower mass stars, and then looking at how that activity changes over time and how that could really affect if there's a big flux of UV radiation or something. Even if the star lives 100 billion years, it's not going to be conducive for life if you have those big UV pulses happening all the time. So that is something that we're going to consider
Cool. So the second question is, when you change the oxygen abundance, does it affect your stellar evolution model, or would that affect your, say, planet atmosphere model as well?
Sorry, would it affect what?
So you change the oxygen abundance in your model. Am I getting this right?
Yeah, so if we change the actual amount of oxygen and nothing else, so everything else stays maybe solar.
Yeah.
And then sorry?
Sorry, and then the major effect is on the stellar evolution.
Yeah, so the major effect is the lifetime and the luminosity. So, and that's just due to what I was talking about with the opacity and the energy transport. If you have more oxygen, you're going to have more stuff bumping into the photons as it tries to escape. So you're going to have less efficient energy escape. And so the energy is going to stay in the star longer. So it's actually going to let the star live longer than it would if it was just all radiating away really quickly.
Yeah, I was wondering, will that change your planet atmosphere and the efficiency of trapping heat as well?
I guess, I'm not sure. I guess that would depend on the planet atmosphere, right? So I don't know if that would directly affect, it would just, from this kind of analysis, it would affect the temperature for sure. So the surface temperature of the planet, but then it would also depend on whatever atmosphere properties the planet had, I guess. I don't know if that answers your question, but.
Yeah, we can talk more later.
Okay.
Thanks.
Yeah.
All right.